So the main thrust of this lecture series is trying to communicate some general principles I've learned and have been trying to apply and generalize to sort of concretely, I want to say represent, and I think if you were writing the abstract to a physics paper, you'd say you want to understand line operators and higher extended operators in at least partially topological quantum field theories. Coming from a physics perspective, but trying to connect with mathematicians, the typical problem I'm faced with is that I have some description of a quantum field theory that I know how to access via some sorts of computations, typically correlation functions of some kind. And maybe that field theory is given to me via Lagrangian, maybe it's given to me via very indirectly by saying, there's some compactification in higher dimensions of string theory, or there's a brane construction, or something like that. That again comes with computational tools. And I know that the theory is supposed to behave at least partially topologically, and thus it's going to have categories of extended operators, and then I want to talk to mathematicians and say, these categories are blah, and they have these properties, and want to compute what these things are. And so it's very useful to develop concrete ways to do that. And it's not just me. Maybe a classic famous example of this problem was Chern-Simons theory. Topological quantum field theory has Wilson lines. Great. How do you figure out how to classify what the Wilson lines are, how they tensor together? In other words, how they collide. And Witten solved this problem by introducing a holomorphic boundary condition, so related to work of many other people at that time. Should in particular mention Warren Seiberg. Introducing a holomorphic boundary condition, letting line operators in the bulk end on that holomorphic boundary condition, and using that boundary condition to sort of probe the line operators, and using modules for a boundary vertex algebra and conformal blocks for that boundary vertex algebra to get information about the category. And then Reshtikin and Turayev sort of guessed that the answer should have something to do with quantum groups at roots of unity, and then Kashtan and Lustig made a bridge between the array representation theory and quantum groups, and the story went on from there. The sort of general mathematical methods for taking some abstract category and making it concrete go under maybe the vague name of categorical representation theory, or reconstruction theory, or Tannakian ideas. And so part of what I want to talk about is just how to import Tannakian ideas into physics. And this has been done for a long time, and I've maybe contributed a tiny bit recently that just generalizes things that have been done for a long time. But I find it very, very useful to sort of group together and systematize this procedure. In the first lecture, I'm actually not going to be talking about line operators. I want to build up some basics and some language and some techniques. Line operators are one-dimensional things, and so the first lecture is going to be about one-dimensional physics. And about two sorts of things in one dimensions, about deformations in 1D, which can be used to take something you know and build something new, and also about perturbative theories in 1D, and a bit of sort of complementary to Alberto's talks, a bit of BV formalism in 1D, which is just a source of useful examples. Part of what I'd like to do is connect sort of like discrete, finite, semi-simple examples and concepts to continuous, infinite, perturbative DG sort of examples that all they're all quantum field theories and in broad strokes should be analyzed in a very similar way. And I'll maybe try to explain what I mean by that in quantum mechanics. Okay, so suppose we have of 1D quantum field theory, and I do want to assume it's topological for now. 1D topological QFT, so topological quantum mechanics. How can we deform it? To get a new one? Well, one way to approach the problem is to abstractly try to define what topological quantum mechanics is. And the only really invariant data that you've got abstractly is a vector space of states. And an algebra that is either NV or some subset of NV acting on it. And I think of A as local operators. There's always a picture in my mind of sort of the vector space going up and operators in the algebra acting at points, and maybe some in-state and some out-state. And what do you do with this data? You build correlation functions, and so a picture like this with an in-state and an out-state and some things inserted in between, I might also write as a correlation function of local operators, say A2 at some time t2, A1 at some time t1, in in state v in and out state v out, where what I actually mean by that abstractly is the linear product of v out and a2, a1, v in. And why do I split it up like this? Because if you actually have like fields and a path integral, maybe formulation, the functions of your fields, the local operators, are actually inserted at points, and that's the thing you take a correlation function of. The simplest deformation of something like this, simplest finite deformation, is what is probably well known to at least some of this audience, because you talk about it in this symmetry game. So it's a condensation. Let me remind you what a condensation is. So the simplest deformation is given by some element in the algebra. And how do you actually deform? Well, you say that your new correlation function the M-deformed correlation function is going to be obtained by inserting M everywhere. Inserting M's everywhere. And for that to be well defined, you can insert M's everywhere. You might also just insert two M's, or one of your A's might be the identity operator, and you want to make sure that, say, if you have something like correlation function of A times 1 deformed, that's the same as a correlation function of A deformed. But if you work out what that is, that's something like M, A, M1, M. That's M, A, M. And for these things to be equal, you need M squared to be equal to M. Which, and this language just tells you that M is a projection. And so the effect of the deformation is to project. It projects the vector space to the image of M, and it projects the algebra to the image of hitting with M on both sides. And do I need to switch the boards? Do you want me to switch the boards? so the simplest dumb example that maybe everyone knows is finite group gauging. If G acts on V, in other words, if the group algebra of G is embedded is embedded in A, then you just let M be a sum of group elements, and then the projection just sends V to the quotient and A to the double-sided quotient. Okay. Great. So that's hopefully all familiar. So what about a continuous symmetry?
It sounds like this kind of condensation procedure doesn't give you anything new. It doesn't have any actual freedom, new freedom. It always comes from low-dimensional thing. And basically just put them together to make it
I agree. So there is some family of, that's right. So there are, right. In my mind, there's sort of a generation procedure here. So a thing you could ask is, given one quantum mechanics, what can you get from it? And you can condense. I would say you should allow yourself to do a little bit more. You can tensor with trivial theories and condense. I guess in quantum mechanics, there isn't much more to it than tensoring with a trivial theory in the topological world, because all you've got is a vector space. Actually, topological quantum mechanics is really stupid. All you've got is a vector space. And this becomes interesting when the line I'm drawing is embedded in higher dimensions. So you have a complaint that you don't get anything new, but you didn't really have very much to start with. I'll comment on your question when we get to higher dimensions.
Sorry. What, here, are you assuming M commutes with Hamiltonian?
Sorry?
Are you assuming that M, the projection operator M, commutes with Hamiltonian?
I'm assuming that the Hamiltonian is 0. I'm assuming much more. Okay. But yes, if you had physical quantum mechanics, you absolutely would need to assume that M commutes with the Hamiltonian. And then Chen Yu's question would actually make sense. And you could ask, given physical quantum mechanics, what family of other things can you get by doing this? And there's some small family, and you're sitting in some orbit of those things, and yeah. It's sort of a small operation. I want to talk about the continuous analog of this, which again might be known to a disjoint subset of you guys. For concreteness, suppose continuous analog. Suppose that our topological quantum mechanics, and I I keep saying topological. For a lot of this, you really don't need to assume topological. This is deformation theory of quantum field theories. Suppose what we have comes from an action. So an integral of some Lagrangian density of some fields along the real line, then deformations correspond to interactions that can be added to this. That satisfy some properties. And the properties you need, well, if I require that the original theory was topological, the interactions need to preserve that. Or if the original theory obeyed some symmetries and I want the deformations to obey them, I need to figure out what that means for the interaction. And there's also something kind of funny in the classification. There's something funny but actually really important. These only matter up to total derivatives. And so, yeah, why do I say that? Because this sort of procedure deforming a field theory makes sense even if you don't have an action to start with. I'll say this a little later. Let me explain what happens to correlation functions when you do something like this. So schematically, adding that, so this modifies correlation functions. Presence of the interaction to the following thing. And it's sort of easier to draw than to write the equation for. So naively, you want to say the correlation function is just the expectation value in the presence of e to the action. And you're adding this term to the action, and so you're just going to take the correlation function and throw in e to the interaction. Fine, but that's not actually entirely sensible because you shouldn't be integrating, you need to regularize. You shouldn't be integrating this thing across the positions of the operators. And so the actual answer looks more like this. What's the red? The red are little insertions of the integrated deformation on segments from like T1 plus epsilon to T2 minus epsilon. And from T2 plus epsilon to wherever you go. And from like minus infinity to T1 minus epsilon. And so the deformed correlator has a bunch of insertions of sorry, have I actually said that right? I think I have. It has a bunch of insertions of this deformation that can never hit the operators that you started with. It's got an integral from t2 plus epsilon to infinity, a2. Integral from t1 plus epsilon to t2 minus epsilon. T1, and so on. That's the actual definition. And so it actually looks very similar to what I did there. And so continuous gauging, I should say, is exactly this sort of deformation. If you want to gauge a continuous symmetry, schematically, what do you do? In some quantum mechanics, well, first you tensor, and this is not just true for quantum mechanics, this is true in any field theory. You can think of it as tensoring that field theory with pure gauge theory. Overlap them with no interactions. And pure gauge theory has a field that's the connection. Quantum mechanics has an operator that's the current. And then you add an interaction. That's the connection times the current. And the integrated deformation coming from that is at least infinitesimally is the gauging. There's a non-perturbative thing that comes from summing over non-trivial bundles that you don't need to worry about in 1D, but you do need to worry about in higher dimensions as well. Okay, so having said that, the idea of deforming by adding interactions and modifying correlation functions like this now makes sense even if you don't have an action to start with, and you don't know what the fields are. You can play a game like this if you just know the operators, the theory, and have just some abstract way to talk about operators. So this makes sense. In terms of operators alone. And by this, I mean the effect of infinitesimal deformations of the action on correlation functions, even if you didn't have an action to begin with. This expression still makes sense, because these are all operator insertions. And that's where this weird thing about total derivatives starts to play a role. The deformations are not just classified by operators preserving some symmetries, but it's operators up to total derivatives that you can integrate. So one can then dive down a rabbit hole and try to classify these things, and people have. but to actually classify deformations and figure out the constraints that they have to obey, one needs a good formalism for QFT to work in. And there are options. One that is useful, especially in perturbation theory, but also occasionally non-perturbatively, is BV. And a lot of the examples I will give later, the easiest way to describe them to someone who doesn't know all the intricacies of like some number of supersymmetries and some dimensions and how to twist it is to just write down a BV action without knowing anything about supersymmetry. So I do want to say a few things about BV. And I think my formulation is going to be a bastardization of what Alberto is doing. The basic things you need to know.
Sorry, I have a question on this picture, because if the QM is topological, it doesn't matter where I put the insertions.
As in, yeah, as in you should be able to contract these to points.
Yeah, like the intervals, maybe I can move them around, stretch them, things like that, it shouldn't change.
I agree. And still get something non-trivial. Yes. I might have done. Yes. Let me say something better about this. That. So just as I was writing it down, I was a little worried. I may have oversimplified the formula too much. Sorry. There are all sorts of funny things going on, and some. And there are little boundary terms around that might not be topologically invariant and matter, and the overall correlation function is still topological. There are funny things happening everywhere, and constraints to solve. Let me write down the correct thing, which I think is equivalent to this. What you should actually do is do a path-ordered exponential of the entire interaction, and then regularize to make sure that the terms in the path-ordered exponential never hit the inserted operators.
Okay.
I think that's equivalent to this. And I am not entirely positive that you can always just squeeze and deform these intervals. Even in a topological theory, everything, especially when you're perturbative, and I'll explain in a second, things might be topological up to equations of motion. And the equations of motion are important. They give you all sorts of boundary terms that you need to pay attention to. So these little intervals, if you contract them to a point, are not actually quite trivial.
Also understanding which sense the example gives a topological theory again. Like in general.
Sorry, no, it doesn't need to be. Like this prescription is deforming any deforming any QFT. You put extra constraints on it to make it topological.
Do you have to carefully redefine your operators when the cutoff epsilon goes to 0?
And you, if it wasn't quantum mechanics, you would. need to very carefully do that, and in quantum mechanics you just take limits, because there are no actual singularities. Yes. Thanks. Okay. So what I mean by BV. First, I'm going to be working in theories where the fields or operators include both bosons and fermions. Which means that all vector spaces and algebras around have a Z mod 2 grading. So there's a fermion number or parity grading. Also, there is an a priori independent. So BV is a cohomological thing. You see it in BRST gauge fixing. And so there's an a priori independent cohomological grading around. So there is also fields and operators have a cohomological grading or a ghost number that I'll call R for, I'll explain why later. That is, in very nice cases, Z valued, but in less nice cases, Q valued, and sometimes R valued. That comes from some other symmetry. And sometimes it is broken to Z mod 2, and often, but not always, fermion number is R mod 2, but R can be more general than that.
Could you quickly give an idea how I should think about like a continuous ghost grading, like a real valued ghost grading?
I'll give you examples.
Okay.
Yeah. It typically comes about when there's another global symmetry in the problem that can be used to continuously shift ghost number. It's the examples where it actually becomes important and are three-dimensional, and so I'll maybe get to them at the end of the lecture on tomorrow.
When do you get like Q or R ghost gradings? In what context do you get Q or R cohomological?
What I specifically have in mind there sorry, I'll say the thing I actually have in mind, which is twists of supersymmetric theories, where this comes from a U&R symmetry, but it's almost never actually U&R, it's a universal cover, and R charges in supersymmetric theories often end up being irrational things. Sorry, I'm forgetting what sort of answer might make you happy. There are interaction terms one can introduce in a theory. Suppose you have, there are interaction terms that need to have, say, ghost number that is equal to 2. So superpotentials and two-dimensional models are of this type. And if you end up with a superpotential that is something like x cubed, and the thing needs to have ghost number 2, you have two choices. You can either well, you can either give up ghost number, or in other words, just reduce it mod 2, and say we're just going to have a Z mod 2 graded theory, or you can give your field ghost number 3 halves, which is the more sensible thing to do.
You also have some real, like, irrational gradings?
And there are irrational things that come about in the same sort of formally. There. Yeah, sorry. I think it's. Sorry, it's really weird mathematically. I should say, like, I'm just throwing this on the board. I almost never see in like mathematical formalism for DG algebras, like homological degree and parity being different. But they can be. It's very easy to generalize the formalism so that they can be. And when you're coming from physics examples, they very often are different. And there's no reason that they shouldn't be. And when you're working with three-dimensional theories, they almost always are different. So this is going to make some things a little bit weird, and you might also just ignore it completely and just think this is a side remark. Anyway, sorry, and there's a BRST symmetry. So I'm writing down the symmetry generator. What I actually mean is that there's a symmetry algebra with that relation, and Q is odd and has degree 1. The feature of BV is that equations of motion are imposed cohomologically. And the way that happens is that the fields are paired up. Roughly, one works in a first-order formalism. And each field or operator is paired up with an anti-field. But in what I'm going to describe, the difference between fields and anti-fields is not really essential. The corresponding operators, in other words, evaluating these things at a point, have opposite parity and cohomological degrees that add up to 1. And what I mean by equations of motion being imposed cohomologically is that whereas in standard physics, you'd write that the variation of the action with respect to either to anything is 0. In BV, the variation of the action with respect to one of these things is Q of the other one. And it's true the other way as well. And so imposing equations of motion is done in a cohomological way. There is this, on the face of it, is just a convenient way to reorganize field content and be a little more careful about what's going on in correlation functions. One of the things that's very useful about it is that it suddenly lets you say with care.
Usually 1 minus 1 there, right? Was according to your convention.
No, I don't. I went back and forth about this. So.
But then that doesn't work, right?
Well. So. There. Maybe this is just my background. I think in terms of operators, which are like functions of the fields, yes, and have opposite grading. And like everything in life happens with correlation functions of operators. And they're the things that symmetries operate on, and there's somehow the things that I actually compute with and care about. And I think these are the correct charges for operators.
But then the question doesn't work.
It's not. The action has degree 0.
Yes.
If let's do this one. If x has, as an operator, has degree r, u has degree 1, and yeah, I probably screwed this up. Yes, thank you. C has degree -1 minus r, and I'm going to subtract this because I'm removing it. So I totally do want an operator equation. Thank you. Okay. Also, this is clearly something I get confused about all the time. Also, people talk about. Yeah. Okay. Anyway, thanks. I totally want that. So one of the huge advantages of this is that it lets you be very careful about what you mean by a topological theory. So if in addition, a QFT is topological, what that means is that I'll say what that means and then explain why it's the right thing. The operators organize themselves in descendants. In other words, for every local operator A, there's an A1 such that Q of A1 is a space-time exterior derivative of A minus the descendant of Q of A. That's the descent equation. And if in 1D, you can stop there. In higher dimensions, you can keep going and define a kth descendant as recursively as the first descendant of the k minus first descendant. The Roland life of descendants is to make sure that correlation functions of Q closed operators, which are sorry, let me also say this better. Because the equations of motion are imposed cohomologically, when you talk about local operators, you don't want to take all of them. You want to take cohomology of Q. So physical local operators are Q cohomology. And the things that need to actually be topological is not all local operators, but just the Q cohomology. And the way to impose that the Q cohomology behaves topologically, one way to do that is to require descendants to exist. The existence of descendants guarantees that correlation functions of Q closed things, which represent equivalence classes of physical operators, are actually topological. And again, by D here, in one dimension, I mean space-time exterior derivative. And this is an exercise that everyone should go through. So for example, if I vary the position of a correlation function of two things like this, and they're both Q closed, then that's the A. And by the descent equation, since they're both Q closed, I can just write that as Q of 1, and use the fact that Q is a symmetry to get 0, which says infinitesimal variations of positions are 0. And now I'm going to go back to your question about why I can't just contract intervals over here. Because when you're working in a perturbative continuum theory, or not even perturbative, just in a continuum theory, it may not be true that topological invariance holds on the nose. It typically only holds up to equations of motion, which can throw in extra terms everywhere. In BV, equations of motion are taken care of cohomologically, and you get phenomena like this. So, like, okay. Let's see, maybe 5 minutes. I want to give you an example of a theory like this, and why it's nice to introduce this formalism. And very quick. So simplest topological quantum mechanics you might write down with a finite Hilbert space is a topological fermion. So take the algebra to be generated by two fermions, psi and psi bar, that have an anti-commutation relation, which I'll still write with square brackets because signs are being suppressed everywhere. And they anti-commute to 1. And so they're both odd. And in order for that to work, they need to have opposite homological degrees. And it doesn't matter what the homological degrees are. Q is 0 because these are the physical operators. I'm just formulating, sorry, I don't even need to talk about R, I'm just formulating a topological quantum mechanics. They act on a vector space that I can just take to be functions of, say, psi, where psi bar will act as derivative. A two-dimensional vector space. So that's abstract. If I want to promote that to a field theory, I need to think that psi is the function of some field at a point, and then I need to make it topological. To make it topological, I need to make sure that as an operator that doesn't vary in time, and so it needs to have an equation of motion that keeps it constant. And the way to do that, in turn, is to add descendants. So I'll add a descendant psi 1 and psi bar 1, such that Q of psi 1 is deep psi, and Q of psi bar 1 is deep psi bar. And they all fit together in an action that ends up looking like this. And I might have, I think that's right. That more conveniently is written in the following form. If I group the descendants together with their primary fields into, I'm going to do blackboard bold psi, together into multiforms. So that's it's a multiform on R. And I group psi bar from psi bar 1 to some other multiform on R. And I can just write the action as psi bar. So that's sort of how to promote a very simple, trivial-looking system to a continuum field theory. We can do exactly the same thing with bosons. In fact, if you want to do the same thing with bosons, you just change the parity of everything on the board. And then the anti-commutation relation becomes a commutation relation. And the second half of the lecture was going to be about what equation these deformations need to satisfy in this very precise context where I actually have a handle on what it means to be topological. And that's a more Cartan equation. And I do want to write that on the board, and I will explain it tomorrow. So I want to say what actually happens. So deformations end up taking the following form. Delta S in a topological theory in BV, where equations of motion are imposed cohomologically, deformations must be of the form of an integrated descendant of a thing. The thing that's being descended is odd and has homological degree 1. That is so that its descendant is even and has homological degree 0, and is a 1 form so that it can actually be integrated. And the equation it needs to satisfy is a Morra-Cartan equation, which is that Q of mu plus mu squared plus some higher terms that are relevant in the A infinity world, but not in quantum mechanics, is equal to 0. And that's the direct A infinity analog, that's the direct continuous analog of the thing I wrote on the board before, which was just the projector equation in the finite case. So I'll say more about that tomorrow.